All right, so the next thing we need to talk about is strong and weak electrolytes. So as we talked before, electrolytes just mean that substance is something like sodium chloride that when mixed in water results in a conductive solution, which means there are free ions in it. So the way this works is shown by this. So we've got solid sodium chloride, and when it is dissolved in water, it actually splits up into individual or isolated sodium ions. Well, not isolated, they're surrounded by water. That's what that aqueous means, and chloride ions. The important thing to know here is that there are no more intact NaCl units in there. It's just sodium ions and chloride ions. And the process that we call this is, specifically, it's called dissociation. So these ions become dissociated from each other in the process because of their interaction with water. Now, unless you are talking about truckload quantities into a gallon or so of water, all of the sodium chloride is going to undergo this process. You will have no NaCl units, it's all NaNCl. And when something does that, we refer to it as a strong electrolyte. So what are these electrolytes? And now they're giving some example. Now, it turns out that there's another that can happen. With the sodium chloride, I would hope that it was obvious how ions get there because it's made of charged particles. Now, it turns out that covalent compounds can also be electrolytes, and that they undergo a reaction, usually involving water, that has ionic products. So hydrochloric acid, HCl, is an example of this. HCl is a covalent compound because it's a non-metal pair. At room temperature and pressure, it's typically a gas, and you can bubble it through water. And this is actually fairly neat. And the product of that reaction is, if you want to simplify it, it's actually a proton and a chloride ion. This reaction is sufficiently quick and fast that if you bubble this through not a beaker like this, but a long one that's a beaker that might be about 2 or 3 feet high, the bubbles don't actually get to the top. The HCl gas reacts with the water, and then as it does so, it becomes part of the solution. The bubbles get smaller and smaller and smaller. And if you do this for, if this column of water is like 2 or 3 feet high, the bubbles never make it to the top, which is kind of neat. And then what you've got in there is you've got no intact HCl molecules. It's just protons and chloride ions surrounded by water. But this isn't quite true. And I don't like doing that because the first way this reaction is shown doesn't really highlight the role that water plays. So this isn't just breaking apart in the solution, it's actually reacting with the water. And this equation right here is really telling you what's going on. That the gaseous HCl is reacting with water, and the product is chloride that we saw before, but there's this thing right here that we have not seen a lot yet. I'm going to show you what this is. So this right here is a polyatomic ion called hydronium. And you can basically model it as a water molecule that has a proton sort of attached to it. But that's really kind of what's floating around in there. I think we've talked about this before. I like showing it this way. It's a little more complicated, but it's also a little more reflective of the process that's actually going on. Now, within today's context of a strong electrolyte, what you need to know is that all of the HCl undergoes this. So all of these strong acids, which are all covalent compounds to start with, are also now classified as strong electrolytes. So let me give you a quick review of what you might want to call electrolyte and what you might want to not call an electrolyte. So electrolyte, to review, it is a solution that conducts electricity. And there are basically two kinds. Strong. Now this is a solute that either by dissociation or by reaction, the reaction is complete and the ions are formed in a stoichiometric amount. Now, the fact that I'm listing strong and weak would lead you to, strong leads you to believe that there's another kind, and that is a weak electrolyte. And this is something that, for one reason or another, just doesn't, whatever the process that makes the ions, whether it's just dissociation or whether it is reaction, does not completely occur. And in that case, some ions are formed, but not all of them that should be formed. So we call that a weak electrolyte. And finally, there's a third category, non-electrolytes, and those are things that do dissolve in water, but don't necessarily result in charged particles getting in there. So this would be mostly most of your covalent compounds, things like ethanol, methanol, and sugar do this. So strong electrolytes are typically going to be ionic compounds that dissolve in water, and strong acids. So you might want to go back to lecture, I think it was lecture 13 when we talked about solubility rules. So not all ionic compounds are strong electrolytes. They have to be soluble, and if they are, then they are also a strong electrolyte. Weak electrolytes are typically weak acids, so this would be something like vinegar. And some weak bases, the big one being ammonia is probably the most common one that we see. And non-electrolytes, for the most part, are covalent compounds that aren't strong acids, but do dissolve in water, so things like sugar and ethanol. So one thing that we want you to be able to appreciate is to talk about what actually is in a solution after the solute is mixed with water. And so what I want you to do is think about this for these compounds and talk about tell me what is actually in each one, and write a reaction that would show me how those ions got there or didn't get there. So take a minute and do that, and I will give you the answers on the other side. Okay, so here's the solution. So zinc, this is going to be a strong electrolyte. So let's call this strong electrolyte or strong electrolyte. So zinc chloride is an ionic compound that dissolves in water, and it's going to break apart into zinc and 2 chloride ions. So the next one was potassium nitrate, and that is also a strong electrolyte. It's an ionic compound, it's a soluble one, and that's going to dissociate into potassium ions and nitrate ions. The fourth one was, this is ethanol, and this is a non-electrolyte. So this dissolves in water quite nicely, but it doesn't break apart into anything. It just, the ethanol molecules separate from each other, but they don't break apart. And so if you wanted to show this with the reaction, you could say that you have liquid ethanol becoming aqueous ethanol. Again, that aqueous just means that solute is interacting strongly with water. And the last one was HBr. So this is also a strong electrolyte because it's a strong acid, and that was on your list of strong acids. And the reaction that it undergoes to make ions is analogous to, excuse me, is analogous to the HCl example. So it reacts with water to form hydronium and a bromide ion. Right. So next topic is factors that affect solubility. So let's do that. All right, so what I've got here is now we're going to talk about things that affect solubility. What I have here are two types, or the structure of two vitamins, vitamin A and vitamin C. Now, vitamins are often broken up into two broad categories: fat soluble and water soluble. So, and what you need to understand is that water is very, very polar, and fat is actually nonpolar. So, looking at these structures, which one do you think is much more likely to interact favorably with fat? And which one do you think is much more likely to interact favorably with water? All right, and so the answer is vitamin A is the fat-soluble one, and vitamin C is a water-soluble one. So the structures are kind of critical here. The vitamin A is made up almost exclusively of carbon-hydrogen bonds. You've got this one OH group here to give you some polarity, but mostly it is just carbon-hydrogen bonds, and they are not polar at all. Vitamin C, on the other hand, has a whole bunch of OH groups, which means this thing is capable of, it's very polar and capable of quite a few hydrogen bonds, which is why it is very water soluble. And this is why, in case you've heard, it's very difficult to overdose on water soluble vitamins, because if you take more than your body needs, you just pee it out. For the fat soluble ones, they tend not to get excreted through the urinary system and tend to actually build up in your fat tissue, and that can actually lead to toxicity, but you still have to have quite a bit of it. So the goal here is to kind of figure out factors that would make something dissolve in something else or not. So let's actually talk about the nonpolar stuff, the fat. So this is kind of what fat looks like. This is a generic triglyceride. There is a little bit of oxygen, carbon, oxygen, hydrogen bonds right here, shown right there. But most of this molecule is just a whole bunch of carbon hydrogen bonds. So this is not particularly polar. And so that's why it interacts quite nicely with things like vitamin A and not like vitamin C. So this leads to the very common